Right, on to our opening keynote. Our presenter today is an Associate Professor and ARC Australia Research Fellow in the School of Information Technologies at the University of Sydney. He has had a profound impact on the use of Python as a teaching language throughout Australia. As Director of the National Computer Science School, he has been responsible for teaching Python to literally thousands of school students, and in doing so has helped to create pathways into computer science careers for students diverse in gender and economic ability. Today, he will share details of an important opportunity to bring Python into Australian classrooms. Please welcome Dr. James Curran.
Thank you. So I'm presenting here with a number of different hats on, so I thought I would just start saying a little bit about each hat. So in my regular day job, I work at Sydney University as a researcher in computational linguistics. And I don't just teach Python, but I write Python. Hopefully, a good day is a day I get to write Python. So that's one dimension of where I come from on the Python front. Second, oh, nope, wrong way. Oh dear. This is the problem with these fancy schmick slides going all over the place. Okay, so the second hat is as the Director of the National Computer Science School. Can I just have a show of hands, first of all, who here programs in Python? Good, just checking I'm in the right conference. Secondly, who learnt to program Python at school? Okay, there's a few. And I see a few NCSS students here in the audience too. Can I just have your hands up too, a few NCSS students? Come on, Imogen, I'm looking right at you and you're not going to put your hand up. Come on. So I've been running NCSS for quite a while, and I'm going to talk a little bit more about that in a minute. And the third hat I'm wearing today, which I'm going to say a little bit about at the end, is as one of the founders of a company we've started to get Python programming and programming more generally into schools. Now, the hat I haven't put on the slide is that I was also very heavily involved in writing the new national curriculum. So let me just tell you a little bit about these different things. So the National Computer Science School, first of all, who's actually heard of NCSS, even if they haven't attended? Okay, that's not too bad, but hopefully by the end of that, everyone will put their hand up. NCSS is the largest computer science outreach program out of a university in Australia. In fact, this year we're hoping to cross the 10,000 barrier in terms of the number of students participating in our online programming competition, which would actually make us one of the largest in the world. NCSS has almost been running for 20 years, so next January will be the 20th version of NCSS under a bunch of different names. Because of my involvement with schools around Australia, I was invited to be involved in the Australian curriculum writing process, and I'm going to tell you mostly, this is what I'm going to talk about today, is the new digital technologies curriculum. As I said, I've been writing Python and teaching Python pretty much the whole time I've been involved in my university life. And I suppose finally, the thing I really believe is that every Australian child should learn Python. So who thinks that's a good idea? All right, good. I'd hate to have accidentally turned up at the Node.js conference instead. All right, so let's look at the current state of computing and curriculum generally across Australia. So Australia has this funny situation up until now where each state and territory has had its own version of a curriculum, and therefore teaching programs, textbooks, resources, everything needed to be produced separately for each state and territory. Now, for a country the size of ours, that doesn't make a lot of sense. And if you're a child moving from one state to the other, it's not much fun either. So whatever you mightn't like about the Gillard government, one of the things they did right was to say, hey, this is crazy. We need to have a national curriculum. And so the national curriculum process started a number of years ago. First of all, with math, science, English, and history. You might have heard a bit about it in the news, primarily because subjects like history and English are a bit of a political football. And right now, Christopher Pyne is kicking that football as far away as he can with a review of the curriculum. We'll talk about that review in a little while. Okay, so the good news is that all of the states agreed it made sense to have one curriculum. Now, agreed is kind of a loose term, and we'll come back to a little bit of that craziness in a minute. For me, what was surprising is that initially I thought that IT, computer science, was not actually going to get a Guernsey in the national curriculum process at all. But we were actually included. But to give you a sense of how much government really understands the importance of IT, unfortunately we were in the third phase of subjects. So we were down with PE, with all kinds of things that, yeah, I know. I mean, what programmers like PE? It's kind of an awkward combination. So we weren't up in the top tier subjects. And initially, I think probably one of the main ways I actually got into the curriculum writing process was that I managed to get an article into the Australian complaining about the fact that in the allocation proposed by Curran, IT would get 15 minutes a week in kindergarten. Right? Now that grows a little bit by the time you get to year 9 and 10, which is where the curriculum ends. But it's still nothing like what we would need. And I've been arguing for a lot of years that IT is essentially the new mathematics, and it's at least as critical to be involved in almost any empirical discipline that you have, the computer skills, the IT skills, programming, and you can see what impact that had with 15 minutes in kindy. So, for us, this is an opportunity to also have one programming language taught right across the country as well. And having taught Python for 15 years and gone through a number of versions of Python, I think that it really is an ideal language to be teaching in schools. I'm not going to say too much about that because that's not really just preaching to the choir, but also the orchestra, the conductor, and everyone else in the music process. So, but if someone wants to ask me about that later on, I'll happily talk about why I think Python is great for teaching. All right, so just to give you a little bit of an idea, here are the different learning areas in the national curriculum. And technologies is a combination of the digital technology subject, which is the one we care about, and also design and technology, which is the woodwork, metalwork, industrial arts, home economics, all of those kind of subjects. One thing that I should point out is that the media arts curriculum is where the federal government has decided multimedia would go. So if you did computing at school, there's a fair chance it was actually a combination of a multimedia subject and, well, you know, fingers crossed, a bit of programming and other things. But Curran, in its wisdom, has actually split that off. And that's actually good for us because I prefer the idea of having a clear distinction between the subjects. Now, in addition to having the individual subjects, there are also these things in the curriculum called general capabilities. And the general capabilities are ideas that are, and skills that are meant to go across all of the different learning areas. So in theory, you should actually be learning some of the ICT skills as distinct from computer science across all learning areas. And to give you a couple of examples of that, it's expected that your maths teacher will teach you about spreadsheets. It's expected that your science teacher will teach you about databases. Probably not SQL, but databases in some form or other. And it's expected that your English teacher will go through using Microsoft Word. So this is both good news and bad news. The good news is that it's no longer the IT subject's responsibility to do those things, right? And that is good to have that clear distinction. Because I have to say, one thing I've noticed in my professional life, if you turn up at a party and say I'm in IT, then that could be everything from a professor of computer science down to someone on help desk. And no one really sees, because we have such a huge range of careers, really sees the whole range. So I think one of the great things about the new curriculum is it actually gives us a distinct area to talk about the hard and cool stuff. So the ICT capability is one of those. Unfortunately, we couldn't call it IT literacy because apparently you can't have literacy twice in the list. And since regular literacy has to be there, then we got a dumb name. Speaking of dumb names, digital technologies is not my preference for a name at all. But when you're involved in the writing process, there's a huge amount of horse trading and negotiating that goes on. And the name, in the end, was kind of the least of our worries in terms of discussing what would be in the curriculum. I hate the plural. What's ironic is I come from a department that also has a plural. Information technologies is equally bad as digital technologies as a name. One thing I would acknowledge, though, is that most of the existing names we've had for our discipline, like computer science, like IT and so on, don't actually resonate very well with people, especially with kids deciding whether or not to do it, with parents and so on. So I'm actually a fan of informatics as a name because I think it covers the broadest idea of managing information and the flow of information and understanding the properties of information. But people weren't too keen on that idea. So the key thing about this technology subject is it's actually mandatory for everyone in foundation, which is kindergarten, through to the end of year 8. And it's an elective subject for students in year 9 and 10, which is typically the way it is across Australia already. And up to this point, there's no curriculum being written or even being planned to be written for year 11 and 12. Now, we know that there will actually have to be huge changes in the year 11 and 12 curriculum because the year 9 and 10 curriculum now eats the year 11 and 12 curriculum for breakfast right across the country. So it won't be possible for the states to actually continue with their existing courses without a rewrite of those senior subjects. But unfortunately, there's no agreement to actually do that centrally. And of course, it's crazy to be writing a joint curriculum up to year 10 and then say, fend for yourselves for the last 2 years of school. So hopefully, we can get that changed. Now, for many states, this is actually the first time that there has been any form of formal IT curriculum apart from general capabilities in the primary schools. And so this is a huge change. And what we'll get to later on is actually computer programming is going to start in year 3. And that is going to freak the hell out of pretty much every primary school teacher in the country. And when I say there are opportunities for you to help, this is kind of where I'm talking about. All right, so this is an ACARA, so the Curriculum Writing Authority infographic of how the different kind of ideas come together. So the top level idea across the whole entire curriculum is this idea of creating preferred futures. Now, I think that the particular phrasing of this is terribly bureaucratic, but I like the underlying idea that students should be given the skills that allow them to create a better future than things are now. And I've always thought of programming myself as actually one of the key tools to be able to do that. Within that, then, unfortunately, I think there's a bit of an overemphasis on project management at school level. And if you did, and if you did any computing subjects at school, you probably spent far too much time on a project management kind of stuff, like requirements analysis, like all of the kinds of things that if you're doing some enormous project with 100 people and a multi-million-dollar budget would make sense. But if you're writing the 1000th version of Blackjack that year in year 11 and 12, then you really don't need a 100-page manual for the code. So there's a bit too much project management to my mind, but a lot of the teachers are actually very keen on this stuff because they think it's important to learn early. I think it's more important to get the underlying skills. I don't actually think you can understand project management until you've been on a project that's either failed or gone horrendously close. So I don't even think our undergrads really get project management. So the key idea, really, in the terminology that people are using a lot these days to describe the skills in this course are computational thinking. So can I just have a show of hands? Who's heard the term computational thinking before? Yeah, so you can think of it essentially as computational thinking is kind of a bit of a rebranding of computer science. A rebranding of computer science just to make it have broader appeal to the rest of the world that's not computer scientists and programmers. I don't really think it's any different to what we've been doing for, well, since the 1960s, but it has been set up in such a way that if you think of yourself as a physicist or a mathematician or an economist or something like that, that computational thinking is something that you would be proud to have, whereas being a computer scientist as well is not something you'd be proud to be. Really the key idea is to frame problems so that they're amenable to computation, which is what computer scientists have been doing since the first time. It's really about having a mindset towards exploiting automation as much as possible. And to me, I actually think this is one of the key things. It's often described in terms of laziness in programmers, the positive laziness. You know, it's actually difficult to explain the idea of positive laziness to school kids. And when you've got a bunch of teachers in the room at the same time, they're like, what the hell are you doing? But you get there in the end. So the idea that actually you're looking for ways of simplifying your work and doing it faster using your brain. And I guess then some more ideas to do with identifying the algorithms, programming a solution, and understanding the limitations of the systems you're building and so on. And to me, I think one of the underlying ideas of all of computer science is really managing complexity. So my take on programming is it's actually the most intellectually challenging thing that humans do collectively. People in quantum mechanics might disagree, but you know. And I think we're still only just starting to understand how to manage complexity. We definitely don't build software on the level of reliability that we build bridges, for example. And if bridges blue-screened of death from time to time, we would be much more unhappy with them than we are with Windows. So these are the kind of core ideas of computational thinking. Now, when you're writing a curriculum, you have to think of the time frame over which you're writing this thing. So we started the writing process 2 years ago, and the shaping paper was written at least a year before that, so 2011. Now, it's highly likely that this new curriculum won't get into New South Wales until 2018, right? And then it will probably run in New South Wales for up to 10 years without modification. How do you write an IT curriculum that has to last for that period of time, right? So let's say 16 years. I mean, that is essentially the dawn of time in computer science past, right? The dinosaurs were running around then. So what we needed to think about is, what are some of the key underlying ideas that will have been true since before computation was actually possible with a computer, and will continue to be true no matter what the computational substrate looks like in the future. So if we're doing quantum computing or whatever technology, what are the underlying ideas that will still be the same? And I'd be happy to have arguments with people later on about what they think those things are. It was a great intellectual process to try and work out what set of concepts you would teach. But here are the ones we came up with. I admit that the last two aren't really concepts as such. I'm really most happy with the first 7 yellow things on that list. So I think that the overarching idea of computer science, and really the main thing about writing code, is management of complexity and abstraction. And I think that that's actually ours to own as an intellectual concept, and no other discipline really teaches that in the way that we do. Maths might have some claim to abstraction, but actually doing it on a practical day-to-day basis, I believe, more lives with us. One of the things you'll see here is that there's actually quite a lot. Specifications, algorithms, and implementation take a substantial time in the new curriculum. And that's one thing that has changed enormously. You'll notice that project management is not a key concept, nor is specification. Yes, well, we're going to talk a little bit about defining problems, but we're going to think of it more in terms of thinking exactly and trying to work out the core parts of a problem, not entirely in terms of let's write 100 pages of requirements analysis in year 8. So the other thing that actually is going to be emphasized a lot in the new curriculum is the idea of collecting and manipulating data. And surprisingly, that has only really got much emphasis in terms of the productivity tools up until now, not actually taking data and manipulating it programmatically to solve some problem in another discipline you're interested in. And there are huge opportunities in the new curriculum, not just to improve computing, but to actually improve every subject by having a bit more of the digital technologies in there with it. And it's difficult to actually exploit that in high school because each subject is essentially a silo that is fiercely protected by the teachers in that particular faculty, and timetabling often makes it difficult to actually have cross-curriculum work. But the new Australian curriculum actively encourages cross-curriculum study. Now, in primary, it actually is all about cross-curricular. In fact, there are so many things in the new curriculum, if you're not teaching 2 or 3 areas simultaneously, you're probably not actually going to fit everything in to the new curriculum in the time you have available. All right, so where is this magical digital technologies curriculum? Well, it has been made publicly available now on the Australian curriculum website, and I've just got a bunch of snapshots of it here. You'll be able to read more in just a minute. So the one thing you can't see at the top is it says available for use, awaiting endorsement. Now, the digital technologies curriculum was essentially ready to go at the beginning of this year. But unfortunately, a change of government substantially interfered with the running of ACARA. First of all, they got chopped into pieces and all of the non-curriculum stuff was removed. Secondly, Christopher Pyne decided that every bit of education needed his loving touch, and that included having a review of the Australian curriculum. Now, the review is being conducted by 2 people that definitely have fairly conservative views about education, but I'm hopeful that they're actually that it's going to have very little impact on what we have in the digital technologies subject. Probably the only good thing about neither major party knowing what to do with us as a discipline and an area of work is that we're not a political football either. So if you were involved in writing the history curriculum, I can imagine that your work may all just go down the toilet in a few months' time when the review is released. But I think that we're going to go through fairly unscathed. The thing that's most likely to change, there's an area of the curriculum called the cross-curriculum priorities, and there are 3 of these priorities. So one of them is sustainability, clearly something the coalition loves. The second one is Asia and our place in Asia. And the third one is Indigenous perspectives. Now, every learning area is meant to actually incorporate aspects of those. And obviously, some can do more or less. For example, we don't have a huge amount to say about Indigenous culture, but we do have things like, for example, sensitivity in collecting photos. So every learning area is expected to kind of incorporate these things. And what I suspect is going to happen is that the review will recommend that those cross-curriculum priorities either get replaced with a different 3 or get thrown out entirely. And that actually won't have a huge impact on us. Other examples would be things like in the curriculum, students are expected to learn about a multi-byte character encodings and Asian character sets and Asian character input methods and so on. Those things can stay regardless of whether Chris Pyne thinks they're a good idea. I'm not sure he knows what they are. So if you want to look at what digital technologies actually is, you need to separate it from the technologies learning area, which is to follow the subjects link I've just highlighted down the bottom there. And it takes you right through to the new curriculum. Now, there are a lot of different ways you can view it. This version here shows you a summary of each year on its own. Then there's this column view that shows you multiple years together. And then finally, there's this detailed view. So the high-level dot points in the curriculum are what are called content descriptors. And then within each of those content descriptors, there's a bunch of elaborations that hopefully explains to a teacher what the scope of that particular idea is and what students would be expected to do. So I'm going to talk you through a bunch of the content descriptors for the different year levels. But the way I recommend you look at it is through none of the fancy web views. They're great for navigating if you're a teacher, but if you want to actually see an overview of the curriculum, there's this handy scope and sequence PDF on the left-hand side here, and we're actually going to go through some elements of that. So each of the key concepts that I spoke about before are highlighted essentially in a line across the curriculum. So the curriculum is broken up into bands, so kindergarten to year 2, year 3, 4, year 5, 6, 7, 8, and then the elective subject in 9 and 10. And as I said, unfortunately no 11 and 12 yet, but we can keep our fingers crossed. Okay, so the first line across is the digital systems line. And if you're in kindergarten to year 2, you'll be expected to identify and use digital systems for a purpose. And the for a purpose is actually quite important because it's very easy just to have kids in kindies mess around with stuff without actually having a particular goal. But by the end of year 2, they're expected to know which particular device it makes sense. You know, for example, one thing you might have seen if you've got young kids is them going up to a TV and trying to swipe it, right? Because every device seems swipeable these days. So, you know, many years ago, when I first started teaching computer science at university, we needed to, actually more like when I was a student, we needed to actually tell some people what a mouse was, right? Now we're kind of the other end of the spectrum where our kids think that everything that's a screen should be swipeable and pressable and so on. So working out what particular devices do and how you can use them is the start of that idea of understanding digital systems. By the time you get to year 10, first of all, an element of security has come into these things, so security and access to network digital systems, and actually understanding the relationship between software and hardware and operating systems and so on. All right, so one of the ones that I'm particularly keen on is the representation of data. I still think it's one of the most amazing things in computer science that everything in the universe can be represented in terms of ones and zeros. And perhaps the biggest downside of abstraction is it's very easy to forget that when you're 75 layers above bits, that actually everything we're doing is a 1 and a 0. I don't expect every child in Australia to love that idea, but I expect every child in Australia to at least be introduced to that idea. So in the year 3-4 band, students will be expected to recognise different types of data and explore how the same data can be represented in different ways. Now this content descriptor in this line actually connects quite well with mathematics because the modern maths curriculum, or the Australian maths curriculum now, actually has quite a lot of statistics and quite a lot of analysis in it, and there's obviously an overlap between these two. By 5 and 6, they'll be expected to investigate how digital systems use whole numbers as a basis for representing all types of data. Now, I sweated blood to try and get the word binary in here and didn't quite succeed in the 5 and 6 band, but we did get at least to the point where kids need to understand that everything is a number inside the computer. And there is an elaboration that talks about binary, and by the time you get to year 7 and 8, they'll be expected to investigate how digital systems represent text, image, and audio data in binary. That alone, I expect, in 20 years' time will save me a substantial amount of time. So as someone that interacts regularly with sponsors and needing both, typically needing a scalable version of their logo and explaining to someone that converting their PNG file to encapsulated PostScript and sending it to me doesn't actually make the thing scalable. Even just being able to do that, my future self will thank me. Yeah. So, okay, so that's representation. The next is collecting, managing, and analysing data. And at the younger year levels, this is really just starting to understand the idea of collecting and presenting different types of data using simple software and trying to solve problems with it, right? Again, there isn't a huge amount of actually using IT to do something in the existing curricular documents across the country. So we've really got an emphasis on actually solving problems and ideally solving problems in other learning areas at the same time. So there's no reason why they can't collect data for geography, for science, for maths, to do the stats stuff. All of that should actually be taught at once, and it would be a lot more fun. So by 7 and 8, they'll be expected to analyse and visualise data using a range of software and use structured data to model objects or events. So that is a slightly less intimidating way of saying you're going to learn to use a database. Ideally, you're going to learn some SQL by the end of year 8. So now, when I say learning SQL by the end of year 8, what we're talking about is the average Australian student, right? There'll obviously be students that will struggle with this, but the goal is to say, well, what do we expect a regular student to do? And the answer is to at least have been exposed to some extent of representing structured data in a way that it can be manipulated and visualized and so on. And we want them to do that with a database. All right, so moving on to the bits I care the most about, creating digital solutions by defining the particular problem, designing, implementing, then finally evaluating the solution. So in kindergarten through to year 2, students will be expected to follow, describe, and represent a sequence of steps and decisions needed to solve a simple problem, or solve simple problems. So a primary teacher in kindy to year 2 is not expected to use the word algorithm necessarily with their kids. But I really believe it's entirely accessible, right? The concept of an algorithm is something that actually every person already knows, but they just don't have the name for it. And so to me, this is actually largely about creating the vocabulary that teachers use to describe things that kids already know how to do. So for example, you ask a kid in year 2, how do you make a piece of toast, right? They can describe that to you. If you get another kid to try and follow those instructions and realize that they forgot to open the bread bag before trying to get the slice of bread out, you've got your first debugging, right? So it's actually quite accessible to do this stuff without a computer, right as far down as kindergarten to year 2. And really getting that idea of how do I describe a problem and the solution to a problem exactly enough so that a system that's not very intelligent can actually apply those instructions is really the kernel of what all programming is about. By the time they get to year 6, they'll be expected to design, modify, and follow simple algorithms in English and diagrammatically, and they basically have to be able to handle the idea of branching and iteration by that point. And, oops, lost a bit on the end there. So by year 10, they'll be expected to do that with more complicated structures and algorithms, and also validate that the algorithms are correct. Now, at this point, we're just talking about algorithms. We're not talking about the actual implementation themselves. So when we get to implementing, well, here's where it gets interesting. So by the end of year 3, the year 3-4 band, students will be expected to implement digital solutions with simple visual programs using branching and user input. So by the end of year 4, we would expect a student to be able to use something like Scratch or Alice or any of those other visual drag and drop environments, and I'm going to show you one of those in just a minute. And be able to do that with some interaction and some user input. By year 7 and 8, they're expected to implement and modify programs with user interfaces, branching iteration functions in a general purpose programming language. What do you think that programming language should be? Right, exactly. So I couldn't get the word Python into the curriculum, you'll be surprised to hear. But when I was thinking about this, I thought, can every Australian child learn to program in Python by the end of year 8, or at least be exposed to it? The answer is absolutely yes. And by year 9 and 10, implement modular programs, choose algorithms and data structures using an object-oriented programming language. Do you think I mean Java here? Right. So I never mean Java, except if I'm saying, why did I get a kernel panic? Then I mean Java. So I believe that Python is the ideal language to teach the year 7 through to year 10 curriculum as one core language. I actively encourage teachers to teach multiple languages, and I think JavaScript is a great combination these days because kids want to do stuff with the web. They want to do stuff that is visual as well. And essentially, I think you're learning the entire stack that you need to do web programming if you get yourself Python and some JavaScript. So I'm not saying only one language, but I'm saying as a core language, we should be choosing one so that we can share resources most effectively. And I think that should be Python. So finally, collaborating and managing, well, all this planning and managing stuff, so I'm going to ignore that. So the key idea is looking at the census data from last year, that every one of our 3.6 million students in Australia will learn to code from year 3 through to year 8 as soon as the curriculum is implemented across the country. You know, I think that is really going to be amazing. Now, who else is doing this at the moment? So there's Estonia, there is Vietnam, soon there will be the UK. So the UK national curriculum starts this September, and they've gone even more hardcore. They don't actually have as many of the other broader information system stuff in their curriculum, and I think that their teachers are all going to die. So I actually think it's important to have a mix. Partly so that the teachers are comfortable, and also partly to recognise that the IT industry is wider than just programmers as well, and just algorithms. But the computer scientists run amok in the UK when they were creating the curriculum, and I think that it's even more hardcore. So, when are we going to get this? Well, so green means almost straight away. So can you see where green is? So the ACT is green. Actually, to be a little bit fair to Queensland and Victoria, there's a good chance because of this review that actually they'll also start teaching it at almost exactly the same time. But formally, it's not the case. New South Wales will probably be the last state to implement the curriculum, except that I've heard recently that WA is looking to use the New South Wales syllabus when it's rewritten, and so they'll necessarily be slightly behind New South Wales, or at least in parallel with New South Wales. So what do I mean for different years? Well, the ACT currently has the most permissive curriculum in the country. You open the document and it essentially says teach computing. In New South Wales, we're at the other end of the spectrum, and we have by far the most tied down curriculum in the country. And so that means writing an even more detailed document, a New South Wales Board of Studies syllabus, before teachers can actually start implementing it, and that's where the delay is. So green hopefully means 2015, right? Red could mean 2017 optimistically, or 2018, or potentially worse, or it could be mangled, right? That's the other thing, is it may not even come out looking like the Australian curriculum. So how can you help with all of this? Well, this is essentially a call to arms for all IT professionals, and actually everyone who's interested in computing within and outside schools. So a curriculum document itself doesn't solve anything, right? It's very easy to go in schools and teach whatever, or teach it badly from a textbook. All it does is give teachers who are engaged and expert the space to teach this material. So if you've got a great teacher, then that teacher's life has just got a bit easier. If you have a teacher who's actually uncomfortable with IT, then your situation hasn't necessarily changed that much, but the political will has changed enormously in that process, and what principals are expecting of their teachers is going to change as part of that process as well, which is why it's the right time to get involved. So essentially, what this is about is that we need you. We need you to go into your local schools. If you've got a child at school already, then that's usually the best place to go, is to go into their school and say, hey, I'd love to run a session. And in my experience, teachers are actually very grateful for doing that in almost all situations. The only thing to be careful of is to make sure you're actually teaching material that's age appropriate and so on. And we've got ways to help you out with that. So what I'm going to very quickly do is talk about NCSS before I finish up, and then give you a 5-second demo of the current NCSS challenge system. So I feel like the summer school and Python have kind of been growing up almost together. So I've kind of interleaved Python versions with the history of the summer school. So Bob Kummerfeld and Judy Kay, who probably taught a number of people here computer science at the University of Sydney, started the summer school sponsored by Unisys in 1996. Had a couple of versions of Python. We first started using Python in the summer school in January 1998 by doing just a little bit of CGI scripting to make what was up to that point just writing web pages, which in 1996 was very cool, right? Most people didn't have, especially most kids, didn't have a modem at home that they could get on this thing, the interwebs. So that was really very exciting for a few years. By the time we got to 2000, oops, a little bit too far. By the time we got to 2000, GeoCities was big enough that actually writing your own web page wasn't that exciting anymore. So for what we did is, with our first news sponsor, CompuWare, we switched to essentially a 6-day team-based cracking competition for classical cryptography. And we had a little bit of Python programming in the lectures, but not a huge amount. The downside was that everyone spent their time writing ciphers and almost no time learning Python. So you take one simple cipher, you modify it the smallest amount you can, and you resubmit until you spammed the hell out of our marking server. So we needed to come up with something that was a little bit more sophisticated than that. We switched over to Python 2 at that point, and the major project for close to a decade was building a search engine and a website for a charity. And then it was a huge amount of Python. And in fact, not only a lot of Python, but probably one of the first Python textbooks out there. In fact, every time I look at a bad Python textbook now, I kick myself for not publishing our notes about 10 years ago, but there were just too many other exciting things going on. Lots more Python releases along the way. We became NCSS in 2005. We have a lot of industry involvement. So last year, for example, we had over 60 industry mentors come along to various parts of the summer school. It's now a 10-day residential camp for about 100 students and teachers around Australia. That year, we also started the NCSS Challenge, our first programming competition. And the goal of the programming comp was to encourage students and teachers right around Australia, rather than just the elite students, to get into programming. Last year, we had 2 years ago, we had over 4,000 participants in the challenge, which was great, but it was getting to the scale where we could no longer manage it just within the university. Unfortunately, the university didn't see it that way, so the team decided that we would start a company to run the challenge on behalf of the university and on behalf of the NCSS sponsors. That company is called Grok Learning. We would have liked to have just called it Grok, but not enough people outside IT know what Grok is, so we snuck learning on the end there. Last year we had over 7,000 participants and switched to Python 3 for the first time, and so now the summer school and the challenge are both in Python 3.3. The next challenge starts on Monday, and we're hoping to have over 10,000 students participate in the challenge. Now, if you're fired up about all of this and want to know how you can help right away, one of the things you can do is help by being a mentor on the forums within this programming competition. So it's a 5-week activity. It's not actually a competition. It's really a 5-week learning activity pretending to be a competition. And at the moment, we have around 50 undergrads who are helping out, undergrads and some postgrads and some industry people. In fact, one Google employee that will remain nameless answered almost 1,000 posts last year. I'm not sure they did anything for Google for that 5-week period, but they helped us out a lot. So if you are keen to help out, please mail challenge@ncss.edu.au or come and talk to me afterwards. And just to very quickly show you what it's about, this is the current learning interface, the Grok Learning interface. Every single example in this interface can be modified and run. And the goal here is so that students learn to experiment with things. And so I'm going to solve this first problem, and the first problem I'm going to solve is Hello World. But I'm going to solve it like a student does. I'm just going to put Hello World in there without paying too much attention to exactly what's required. Now, most auto-marking systems at this point will just go, you've got it wrong, game over. What we do is we actually walk a student through solving the problem piece at a time. So here, we've tested that you've got the words correct, which you have, but we're telling you then that you've got the punctuation wrong. So now, a really good student at this point would go, oh, I need to do this exactly. Many students and their teachers at this point will go, oh, okay, I'll fix the punctuation, not realizing that they also need to fix the capitalization. The white space is right, capitalization, we've got to fix it up. hello world, and we've solved our first problem. Now, at this point, yeah, you don't need to clap me solving hello world. No, you really don't. Yeah, I did it. I was worried. It was close. The thing about it is that it's not just about learning about programming, it's learning to be exact. And I think one of the things that distinguishes everyone in this room from people that are not programmers is the importance of being exact. Now, some people think that's a personality flaw and have other words to describe that. But either way, for our field, it's critically important. And so we're trying to develop that mentality at the same time as teaching the programming. The other thing that I will mention very quickly is this year for the first time is we're introducing a visual programming environment, but with the key difference that you actually see the Python that will be generated that corresponds to your visual program at the same time. So as I live type my hello world in here, if you write programs that are small enough to fit in this screen space, I want to know about your employer. And hurrah, we've got hello world correct in 2 different environments. Oh, really? Another clap? All right, so I'm going to leave it there. If you're interested in being involved in the challenge, please come and talk to me afterwards. If we had a room full of people like this helping kids around Australia, we would definitely be able to scale ourselves to tens of thousands in the next couple of years, and wouldn't that just be amazing? Thank you very much.